Imagine a region that, well, it basically has it all. Abundant raw materials, literally right there in the ground.
Right, massive physical capacity.
Exactly. Massive manufacturing capacity.
Yeah.
Factories churning out everything from, precision forged steel components to packaged foods. Thousands and thousands of skilled workers clocking in every single day.
A huge workforce.
Yeah. But despite this overwhelming physical wealth, the businesses inside this ecosystem are they're completely starving for capital.
Locked out completely.
Locked out of the global banking economy. They can't get loans. They can't expand. They're just bleeding profit margins. And the riddle is, why?
It really is the ultimate industrial paradox, isn't it? Because, I mean, it's not because the machines are broken. And it's definitely not a lack of market demand.
No, the demand is absolutely there.
Mm.
Which brings us to the answer. And that is exactly what we are exploring today. So welcome to another custom-tailored deep dive.
We've got a really great stack of sources for this one.
We really do. A fascinating stack of documents centered on the industrial heartbeat of India, specifically the Vidarbha region and the Nagpur district.
Our mission today is to essentially unpack how physical reality collides with digital finance.
Right, and our sources today range from the macro all the way down to the incredibly micro. We have an official government industrial profile for Nagpur, which just details the sheer volume of these enterprises.
And then we pair that with some dense but really illuminating academic research.
Yeah, the studies by Dr. Pralhad Nagmot and Priyanshu Bist, looking at resource availability and industrial clustering.
And the final piece, which I think is my favorite, is a set of field notes from an actual engineer.
Oh, the boots on the ground perspective.
Sure.
Yeah, this engineer is currently out there, like literally right now, deploying cutting-edge artificial intelligence directly onto legacy factory floors.
The contrast here is what makes this deep dive so compelling, because the government data shows us the scale of the operation, right? And the academics, they show us the structural friction.
A theory behind why it struck.
Exactly. But those field notes, they reveal the exact practical mechanism of the failure. The reason these factories are starving for capital comes down to one phrase from those notes.
The analog bottleneck.
The analog bottleneck, yes.
We are going to spend a lot of time unpacking that today, because what you are looking at is this stark disconnect between physical execution, the actual making of a product, and digital verification.
Which is the only language modern banks actually understand.
Right. If you can't translate the physical reality of a factory floor into a verified digital format, you are trapped.
And we're going to look at the exact technology being used to bridge that gap. How putting localized intelligence on decades-old machinery can fix the balance sheet, but also, importantly, restore human dignity to the workers.
It's incredible stuff. But
Yeah.
to understand the bottleneck, we first have to understand the sheer volume of what is trying to flow through it. Right?
Yeah.
We need to look at Nagpur's industrial engine.
It's massive. If you look at the government's brief industrial profile, it paints a picture of a region just teeming with enterprise.
It is a powerhouse.
Yeah, and if you look at the employment data, they break it down by the National Industrial Classification, the NIC 1998 codes, and it's highly concentrated.
Yeah, I was looking at code 15.
The manufacture of food products and beverages, it's a behemoth. The data shows employment ranging from 10,542 up to 11,459 people.
Wait, just in that one sector?
Just in that specific sector in Nagpur, yes.
I mean, I want to pause on that number because it's so easy to just gloss over statistics. Over 10,000 people. That is not a single massive centralized factory.
No, no.
That is a vast network of smaller operators. People processing agricultural yields, milling grain, refining cooking oils, running bottling lines and packaging.
It's incredibly labor-intensive. And that's just the food and beverage side.
Right.
If you move down to Code 17, which is textile manufacturing, you see over 4,200 people there. Then you've got the foundries, the metalworking shops, leather processing.
Which perfectly brings us to Dr. Pralhad Nagmot's study, because he actually went in and surveyed 175 specific MSMEs, that's micro, small, and medium enterprises, right there in Nagpur.
And his overarching conclusion is that these MSMEs are the fundamental engine of growth for the developing economy. The national numbers he provides are just staggering.
Like what?
Well, he notes that the MSME sector accounts for 45% of the total industrial output in India.
Wow. Almost half of everything physically produced.
Exactly, and 40% of the export revenue. But the really critical detail he highlights is the capital to employment ratio.
Ah, right. MSMEs have massive employment potential at an exceptionally low capital cost. Walk me through the mechanics of that, actually. Why is that ratio so favorable?
Well, think about building a brand new state-of-the-art automotive plant, highly automated.
Okay, like a multi-billion-dollar facility.
Right, it might cost $2 billion to build. And because it relies so heavily on robotics, it might only actually employ 1,000 people. So the cost per job created is enormous.
Right.
But an MSME, let's say a small metal forging shop in Nagpur, might only require $100,000 in capital. You buy a few secondhand lathes, a press, you rent a facility.
And suddenly you're hiring 20 people.
Exactly. It immediately employs 20 or 30 people from the local community. The barrier to entry is low, but the social and economic impact is immediate and profound.
Right. But the other side of that coin, I guess, is that these smaller shops, they aren't producing finished consumer-ready products. I mean, they aren't selling cars directly to the public.
Exactly. And this is a crucial dynamic to understand. These businesses do not exist in a vacuum. They are the essential feeders to the large-scale industries, the LSIs.
The government profile lists some real heavy hitters in the Nagpur district, right?
Yeah, you have Bajaj Steel Industries, San Vijay Steels, ACC Machinery Co., Halderam Food International. These are massive, globally recognized corporations.
You know, reading the sources, the analogy that kept coming to mind was an ecosystem, or like a forest. The large-scale industries, your Bajaj Steels and Halderams, they are the massive, visible redwoods.
I like that.
But the MSMEs, they are the vast interconnected root system, the mycelial network under the soil. They are the ones actually pulling the nutrients out of the dirt and keeping the whole forest alive.
That's a perfect way to look at it. If a single part of that root system fails, the redwood starts to die. The large companies rely on this perfectly timed flow of parts.
Right, the foundries forge the brackets for the heavy machinery.
And the packaging plants print the corrugated boxes Halderam needs to ship its food. The large company handles the final assembly and global distribution. But the granular manufacturing is entirely dependent on the MSMEs.
So Nagmo's study shows that 60% of the authorities he surveyed believe there is a strong possibility for even more employment generation here.
Oh, absolutely. The potential is huge.
The region has the workforce. It has the heavy-hitting buyers waiting for parts. But as we mentioned at the start, growth has stagnated. So the obvious assumption, and I think what most people listening would assume, is that they must have run out of resources.
Right. No raw materials or no electricity.
Exactly. They hit a physical wall.
But that is the most common diagnostic error when looking at industrial stagnation. You assume a physical bottleneck, but the data from NAGMO completely shatters this illusion of resource scarcity.
How so?
When he surveyed these local operators, a massive 67.4% of them stated that resource availability was, quote, easy.
Wait, I have to challenge that a bit. Easy is a really subjective term.
Yeah.
Especially on self-reported surveys. Like, are they just used to a certain level of hardship, so they call it easy? Or is the region genuinely flooded with resources?
It's a very fair question. But if we look at the geographical data backing it up, the Vidarbha region is legitimately rich in raw inputs.
Okay.
They have direct access to high-grade coal, manganese, iron ore. The agricultural baseline for the food processors is deeply established.
Right.
They have the roads, the power grid, the physical factories.
And the physical abundance is real.
It is real. That 67% figure isn't just optimism. They literally have the steel, the power, and the people.
Okay, so if the physical inputs are abundant, what about how these factories are organized? Maybe the engine is built, but the parts are just, in the wrong place. Which brings us to Priyanshu Bist's research on industrial clustering.
Yes,
And honestly, this involves some pretty heavy math.
it does. Bist uses graph theory to measure economic interconnectedness. He's not just looking at geographical proximity, like how close factories are to each other.
Right.
He's measuring how tightly they interact operationally. He compares different regions in Maharashtra. For instance, he looks at the Konkan region and gives it a cluster coefficient, which he calls K of 8.33.
Okay, and an economic indicator, Helen, of 11.98. But I don't want to just throw numbers at you, the listener. What is the actual mechanism being measured by a cluster coefficient of 8.33? How does BIST calculate that?
Let's visualize it. Imagine every single business in a region is a dot on a massive whiteboard. These dots are nodes in a network. Now, every time one business interacts with another.
Like a transport company delivering steel to a foundry.
Exactly. Or a local accountant servicing a packaging plant. Every time that happens, you draw a line connecting those two dots.
So you're mapping the actual real-world supply chain linkages.
Right. The cluster coefficient is essentially a mathematical ratio. It measures the number of actual connections between these dots compared to the maximum possible number of connections if everyone interacted with everyone else.
Got it. So a higher number.
Like Konkin's 8.33 means the dots are heavily interconnected. It's a dense, tangled mesh network. If one supplier goes down, the factory has 3 other local lines connected to it. Resources, information, and capital flow incredibly fast in a high-density cluster.
It's highly fluid, very resilient.
Yeah.
But then BIST runs that exact same math on Nagpur and Pune, and the pattern is completely different, isn't it?
Drastically different. Nagpur leans heavily toward being a large enterprise hub. Remember the redwood analogy? Nagpur is great at hosting massive redwoods. The physical infrastructure supports the large-scale factories. But when BIS looks at the MSMEs, the roots he finds their clustering coefficient is incredibly low.
Meaning they aren't drawing lines to each other on the whiteboard.
Exactly. They're operating in geographic proximity, but operational isolation. They run on a hub-and-spoke model.
So every small MSME only talks to the massive, large-scale industry buyer, like Bajaj.
Yes, but they don't collaborate or share data with each other. The text specifically notes they operate without a cohesive data feedback loop.
And a major reason for that isolation is the machinery itself, right? These MSMEs are running legacy equipment.
Very old equipment, yes.
Heavy, durable cast iron lathes, mechanical presses, equipment built in the 80s or 90s. It works perfectly fine physically, but as the engineering field notes point out, this machinery is entirely deaf.
That is the perfect word for it. It is deaf and mute. A modern multi-million-dollar CNC machine has hundreds of sensors. It connects to Wi-Fi.
It's basically a computer that cuts metal.
Right. It streams data about its temperature, output rate, power consumption. But the legacy iron in Nagpur operates in total digital silence. The only way to know what that machine is doing is to have a human being physically stand next to it and watch it.
And here's where the riddle we posed at the beginning of the deep dive snaps into focus. I am an MSME owner. I have the steel, which is easy to get. I have the workers. I have a factory full of heavy machinery. And I have a huge corporation down the road ready to buy my output.
All the physical pieces are in place.
Yes. So why do the engineering notes tell us that nearly 40% of local operators in this exact situation are struggling to secure basic finance from local banks?
Because of how banks assess risk in the modern era, the true structural failure is not a physical constraint. It is a documentation constraint. The bottleneck is verifiable process data.
Let's really dig into this hidden cost of manual compliance. Because the engineering notes describe a situation that just sounds completely maddening. They call it a blame game.
It operates more like a standoff. The factory owner goes to the local bank and says, look, I have a massive purchase order from Helderum. I need a capital loan to buy raw materials to fulfill the order.
Right, guaranteed business. Give me the loan.
And the bank looks at it and says, we see the purchase order, but we need to verify your operational capacity. We need to see your safety logs, your production efficiency data, your maintenance schedules.
I want mathematical proof.
Exactly. Proof that you can fulfill this order without burning down your factory or going bankrupt.
So the factory owner hands the loan officer a massive stack of handwritten clipboards, smudged pencil, coffee stains, missing pages.
And the bank immediately denies the loan, or they charge an exorbitant interest rate to offset the massive risk of the unknown.
To explain this, the notes use a phrase that I think is fundamental to understanding industrial economics. Quote, when processes require manual verification, risk scales linearly with production.
Yes.
Walk me through the actual mechanics of that scaling risk. Why is growth actively dangerous for these companies?
It comes down to human limitation. Imagine you run a small shop, you have 3 machines. You, the owner, can personally walk the floor. You look at the temperature gauge on the forge, you write it down on a piece of paper.
And I know it's accurate because I did it myself.
Exactly. The risk of that data being wrong is very low, manageable.
Okay.
Now, let's say you get that big contract. You need to expand. You hire 50 new workers, you add a night shift. You physically cannot be on the floor 24/7.
Right.
So now you're relying on 50 different people who are exhausted, working long hours in a hot, noisy environment, to accurately read analog gauges and write them down on clipboards every single hour.
The probability of error just goes through the roof.
Risk scales linearly with production. For every unit of product you make, you create a unit of manual paperwork. People misread dials. They forget to log a safety check because they were rushing to fix a jammed gear.
Or they just guess.
Or worse, the incentive structure forces them to lie. If a worker knows taking a machine offline for maintenance will cost them their Stift bonus, they might just forge the temperature log and pretend everything is fine.
I really want to emphasize that point for the listener. It's not necessarily malicious fraud.
No, not at all.
It's survival instinct in a high-pressure environment. You just want to keep the line moving, so you pencil whip the safety log.
But the bank knows this. The insurance companies know this. They know a handwritten log from an unair-conditioned factory running 3 shifts is essentially fiction. They cannot mathematically verify a single number on that page. And in finance, unverified data equals maximum risk.
I use this analogy a lot, but it perfectly explains the mechanism here. Imagine you, the listener, trying to get a mortgage to buy a house. You walk into the bank. Usually, the underwriter pulls your digital credit report. They hit an API that automatically verifies your income directly with your employer or the government.
Right. They look at automated digital bank statements. The data is instant, cryptographic, and perfectly verifiable.
The loan officer doesn't have to trust you as a person. They trust the digital infrastructure.
Exactly.
Now, imagine walking into that same bank with absolutely no digital footprint.
Right.
Instead, you hand the loan officer a shoebox stuffed with handwritten receipts on the back of napkins, a torn piece of notebook paper that says, "I made $500 on Tuesday. Trust me."
You would be escorted out by security.
Right. The loan officer would say, "Look, I believe you physically exist. I believe you probably did make $500, but I cannot verify this data. Therefore, my risk is infinite, and your loan is denied."
And that exact scenario is playing out on a massive industrial scale across Nagpur. The physical output is real, but their operational data is a shoebox full of napkins.
And this creates a secondary economy that bleeds the MSMEs even further, doesn't it?
Oh, absolutely. Because the banks demand verification, an entire industry of intermediaries, auditors, and middlemen has sprung up.
It's translators.
Yes. Third-party auditors who charge exorbitant fees to walk into the factory, look at the messy handwritten logs, and translate them into a formatted report the bank will actually accept.
So the factory owner is paying a premium just to prove to the bank they are doing the work they are already doing. It just destroys their profit margin.
Exactly.
So we've clearly defined the analog bottleneck. It is the friction of manual translation. But what is the cure? I mean, the obvious answer, like the Western Silicon Valley answer, would be to tell these factory owners to throw away their 1980s mechanical lathes and buy $10 million digitally native CNC machines with built-in Wi-Fi.
Which is an absurd proposition. We just established they can't even get a loan for basic raw materials. They certainly cannot secure a capital expenditure for a massive fleet replacement.
Right.
Furthermore, it's incredibly wasteful. Those legacy machines are built like tanks. They have decades of useful life left in the iron.
Which is where we transition into the most fascinating part of the engineering field notes, the concept of restorative engineering.
It's such a beautiful philosophy. The engineer writes that true technology shouldn't demand the spotlight. It must fix broken systems and optimize operations quietly.
Quietly. I love that.
Restorative engineering doesn't mean replacing the old system. It means retrofitting it. It means making the dumb iron intelligent.
And the engineers proposed a highly specific architectural solution to achieve this on these factory floors. They call it the Nano Banana 3 compliance engine.
Despite the whimsical name, the engineering architecture behind the Nano Banana 3 is a masterclass in first principles problem solving. It directly attacks the shoebox of receipts problem using localized artificial intelligence.
Let's break down exactly how this mechanism works, because it requires solving some serious technical hurdles.
The system consists of 3 distinct layers: the hardware, the vision model, and the language model output.
Let's start with the physical hardware. What are we actually bolting onto these legacy machines?
It's shockingly inexpensive. The system relies on a ruggedized, off-the-shelf industrial camera. And this camera is wired directly into a microcomputer known as an edge processing board. The engineer specifies using a Raspberry Pi, or, for more complex tasks, an NVIDIA Jetson Nano.
Okay, for listeners who aren't deep into hardware engineering, a Jetson Nano is essentially a tiny, highly efficient computer, about the size of a thick deck of cards. But unlike a regular desktop computer, it has a specialized GPU built specifically to run AI models locally.
And that word locally is the linchpin of the entire operation. This is what we call edge computing, or edge AI.
Right.
The data isn't being recorded and sent over the internet to an Amazon or Google cloud server to be processed. The processing happens right there on the machine at the edge of the network.
Okay, so we have a camera and a tiny computer bolted to a 50-year-old metal lathe.
Mm.
What is the software actually doing?
The Jetson Nano is running a localized computer vision model. It processes the raw pixels coming from the camera feed in real time. But it isn't trying to understand the whole world. It is highly fine-tuned to track just 3 specific variables on that factory floor.
And the first is PPE compliance.
Personal protective equipment, exactly. The vision model draws invisible bounding boxes around the workers. It mathematically calculates, is there a hard hat on the head? Are safety goggles present over the eyes?
If yes, it logs a positive integer.
If no, it flags a violation.
Yep.
Instantly. No human clipboard needed.
The second variable is cycle time.
Right. The camera watches the physical movement of the materials. It sees the raw piece of steel loaded into the chuck. It starts a timer. It sees the finished piece removed. It stops the timer. It now has perfect, indisputable data on exactly how long the production cycle takes, down to the millisecond.
But the third variable is the one that really blows my mind, because it basically replaces human intuition with computational precision, machine status.
This is where the vision model gets incredibly sophisticated. The camera isn't just watching the worker, it's intimately watching the mechanics of the machine. It can monitor the tool head vibration.
Wait, walk me through how a camera measures vibration.
It looks at pixel displacement. If the cutting tool is vibrating abnormally because a bearing is starting to fail, the vision model can detect the micro movements of those pixels from frame to frame long before a human operator would feel it or hear it.
Oh, wow.
Furthermore, it analyzes what is called chip formation.
Okay, when a lathe cuts into steel, it peels off these sharp, spiral metal shavings. Those are the chips.
Yes, and the shape, color, and length of those chips tell a story. A master machinist with 30 years of experience knows that if the chips suddenly start coming off jagged and blue, the cutting tool is getting dull, it's creating too much friction and heat, and is about to shatter.
Right.
The vision model is trained on thousands of hours of video to recognize that exact visual pattern. It digitizes the master machinist's intuition.
I really want to push back here on the physical realities of this, though, because I've been in manufacturing environments. They are hostile. You're talking about a factory in Nagpur. It might be 115 degrees Fahrenheit inside.
Air easily, yes.
There is vaporized cutting fluid and highly conductive metal dust floating in the air. A Jetson Nano is a delicate piece of silicon. And running an AI model pushes the processor to 100% capacity, which generates immense heat.
True.
How does this tiny computer not just melt or short circuit within the first hour?
That is the exact engineering hurdle that separates a lab experiment from a restorative engineering product. You cannot just tape a naked circuit board to a lathe. The hardware has to be encased in IP67 rated, ruggedized passive cooling enclosures.
Passive cooling, so no fans.
Exactly. You use massive aluminum heat sinks rather than motorized fans because a fan would just suck conductive metal dust right onto the motherboard and short it out instantly.
Right, and thermal throttling is a huge issue. If the chip gets too hot, it slows down to protect itself, and suddenly your real-time vision model is lagging.
Exactly. So the software engineering has to be incredibly tight. You have to optimize the vision models, a process called quantization.
Quantization.
Yeah, reducing the mathematical precision of the neural network just enough so it runs fast and cool on low power without losing accuracy in detecting a safety goggle or a jagged metal chip. It requires immense discipline in the code.
Okay, so the hardware survives the heat and dust, and the vision model successfully watches the machine. It knows the cycle time is 45 seconds, the goggles are on, the tool isn't vibrating, but that is just raw binary data.
Right.
A bank loan officer doesn't want to look at millions of rows of pixel displacement data.
Which brings us to the final layer of the Nano Banana 3 architecture, the language model output. This is the magic trick.
An onboard LLM.
Yes. A large language model, similar in architecture to what powers ChatGPT, but much smaller and highly specialized, is running directly on that same little Jetson Nano. It takes the tabular data generated by the vision model, the timestamps, the compliance checks, the vibration metrics, and it automatically synthesizes that data into natural language.
It essentially writes a report.
It writes a perfect, unalterable, time-stamped PDF report at the end of every shift, and it formats it exactly to the specific requirements of the local commercial banks and government subsidy programs.
Wow.
It completely bypasses the human with the clipboard. It eliminates the coffee stains, the exhaustion errors, the fraudulent entries. The bank receives a mathematically verified, cryptographically sealed log of factory reality.
The shoebox of receipts vanishes and is replaced by pristine, undeniable digital truth.
Precisely. Now, we touched on this briefly, but we really need to explore why running this entirely on the edge locally on the machine is so critical. Why not just beam the video feed to AWS and let massive cloud servers handle the heavy lifting?
Right. Why the local Jetson Nano?
The text heavily emphasizes the concept of data sovereignty.
Because if I'm a factory owner, my production data is my lifeblood.
Exactly. Industrial espionage is real, but even more common is simple competitive intelligence. If you're constantly streaming high-definition video of your proprietary manufacturing techniques, your cycle times, your defect rates.
Over the internet to a third-party cloud provider.
Yes. You're exposed. You are essentially giving away the recipe to your business.
Plus, in a region like Vidarbha, you cannot guarantee 100% internet uptime. If a backhoe cuts a fiber optic cable down the street and your factory loses internet, a cloud-based safety system goes totally blind.
That is absolutely unacceptable when human safety and machine failure are on the line. With the Nano Banana 3 architecture, because the processing happens locally on the edge, the data never leaves the building.
True data sovereignty.
The factory owner maintains absolute control. The raw video is processed in real time and immediately discarded. The only thing that ever leaves that Jetson Nano is the finalized, encrypted PDF report sent directly to the bank.
This technology is incredible. It perfectly solves the analog bottleneck. But I'm putting myself right back in the shoes of that MSME owner.
Okay.
In Section 3, we established that I am bleeding margin. I'm paying high electricity costs. I'm paying exorbitant fees to third-party auditors. And the bank won't lend me capital.
Right.
If a tech startup walks into my factory and pitches me a multi-layered edge AI vision system with onboard LLMs, my immediate response is, I can't afford that.
And that is the ultimate friction point for deploying new technology in legacy environments. But this is where the engineer's approach moves from purely technical to a brilliant first principles economic strategy. They understand budget gravity.
Budget gravity, I love that term. Money naturally flows toward whatever eliminates risk the fastest.
Right. The engineer's notes explicitly state the golden rule of deployment. You do not sell AI.
The factory manager doesn't care about neural network quantization or bounding boxes.
They don't care at all. They care about their balance sheet. You sell the elimination of compliance friction. So the economic model is completely flipped. The hardware, the camera, the ruggedized enclosure, the Jetson Nano is installed for free.
Wait. I have to push back here on the business model of this tech startup. Giving away highly specialized, ruggedized hardware for free. That is a massive capital burn.
It is.
How does an AI company survive that? What happens if the AI fails or the factory manager just unplugs it after a week because they don't like it?
It is a calculated risk, but it's based on an undeniable value proposition. They offer a 14-day free trial on the factory's absolute worst, most problematic machine. The machine that constantly breaks down and causes the most paperwork headaches.
Yeah.
They bolt the system on for zero upfront capital expenditure. This completely bypasses the factory owner's inability to get a bank loan for upgrades.
Okay, so the hardware is a Trojan horse. How does the AI company actually make money?
Monetization happens through the software output. The factory owner pays a monthly subscription for the predictive alerts and the verified compliance reports.
A SaaS model for heavy industry. Software as a service.
Yeah. Exactly. But here is the genius of the first principles strategy. That subscription cost doesn't actually hit the factory owner's bottom line. It is instantly mathematically offset by the savings.
Walk me through the math on that. How is it offset?
The moment the factory has a verified, unalterable PDF proving 100% safety compliance and predictable machine maintenance, they take that report to their insurance broker. Because the risk profile has drastically dropped, their industrial insurance premiums drop immediately.
That's one offset.
Second, because the AI vision model is watching the chip formation and tool vibration, it stops the machine before catastrophic failure. They save thousands of dollars on scrapped raw materials and emergency repair parts.
Two offsets.
And third, they fire the third-party auditors. They no longer pay exorbitant fees to middlemen to translate their messy clipboards. The subscription cost of the AI is entirely paid for by the elimination of existing friction.
Wow.
The factory becomes instantly verifiable, instantly bankable, and highly profitable, all without a single dollar of upfront capital.
It is a phenomenal alignment of incentives. And it brings us to the broader implications of this whole transformation. Because this localized edge intelligence, it doesn't just fix the paperwork problem. It fundamentally changes the trajectory of the human beings working on that floor.
It really does.
Let's look at the asymmetric advantage, safety, and the concept of tangible hope.
Let's start with the asymmetric advantage. The text states that the early recognizer in the Nagpur region, meaning the first factory owner to adopt this digital verification framework, gains a massive, insurmountable advantage over their regional competitors.
I mean, it seems obvious that being more efficient is better, but let's drill down into why the advantage is so outsized. Why does it compound so quickly?
It comes down to a concept called data latency. Data latency is the time delay between an event happening on the factory floor and management knowing about it. In a manual clipboard system, data latency is measured in days or weeks.
Like a machine starts vibrating on Tuesday.
The worker glazes over and forgets to log it, the machine breaks on Thursday, and the auditor finds out next Monday.
By which point the production line has been dead for days.
Exactly. The text says it perfectly. The factory that can predict a machine failure tomorrow wins the contract today. Data latency is the ultimate control point in manufacturing.
Right. Imagine I am bidding against my competitor for a massive multi-million-dollar contract to supply parts to Bajaj Steels.
Okay.
My competitor is running on the analog system. They have to price in the risk of unexpected downtime. If Bajaj demands a 48-hour delivery turnaround, my competitor might decline the contract or bid very high because they're basically guessing whether their old lathes will survive the week.
They are operating completely in the dark.
But if I am the early recognizer with the Nano Banana 3 system, my AI tells me with mathematical certainty that my lathe is operating optimally. It predicts the tool will not fail for another 80 hours.
You have zero data latency.
I have zero data latency. I can absolutely guarantee the 48-hour delivery. I can bid lower with higher confidence. I win the contract. And once I have that verified cash flow, I take my perfect digital reports to the bank, secure a low-interest loan, and buy my competitor's factory when they go bankrupt.
That is the asymmetric advantage. The validation signal is immediate, and it creates a compounding loop of capital access and operational dominance. Any floor manager will authorize a subscription payment for a system that guarantees an uninterrupted production cycle.
But I want to pivot here, because the most profound parts of these engineering field notes are not about profit margins, or crushing the competition, or even securing bank loans. The notes are deeply rooted in the human element. The technology is viewed through a surprisingly philosophical lens.
It is. There's an anecdote in the text that provides the emotional core for why this engineer builds these systems. It's a memory from years ago, far away from the steel lathes of Nagpur.
Yes, the engineer writes about an experience watching factory workers handle actual, live explosives. They were handling grenades on a manual assembly line.
It is a terrifying image to even think about. The engineer observed that on that specific floor, quote, fear drove the execution. You have human beings doing repetitive physical labor, utterly terrified that a single slip of the hand, a moment of exhaustion or a microscopic distraction could instantly end their lives.
And so, the engineer intervened. But they didn't just tell the workers to be more careful. They built a robotic process. They integrated a Techman cobot.
For context for the listeners, a cobot is a collaborative robot. Unlike massive industrial robot arms that swing wildly and have to be kept in physical cages so they don't crush people, cobots are designed with force sensors to work gently and safely right alongside human workers.
The engineer programmed this cobot to handle the most volatile, dangerous parts of the grenade assembly. And the takeaway in the notes wasn't a celebration of efficiency.
No, the engineer didn't brag about increasing grenade output by 20%.
The financial savings were totally secondary. The ultimate metric of success, the thing that drove the entire project, was the psychological relief of the human worker. The metric was the text message the worker could send home to their family at the end of the shift. I'm safe tonight.
Real technology restores human dignity. That is the recurring mantra throughout these field notes. When you use restorative engineering to eliminate the terrifying, the mundane, or the physically destructive elements of labor, you are not replacing the human.
Right.
You are not automating them into unemployment. You are restoring their capability to do what humans actually do best.
Which is to think, to adapt, to manage the complex edge cases that robots just can't handle. You remove the human from the role of a biological sensor, staring at a vibrating machine, and elevate them to a manager of intelligent systems.
And this philosophy doesn't stop at heavy industrial manufacturing. The notes make an incredible extrapolation that shows the true universality of restorative engineering.
This blew my mind.
This exact same engineer who is building edge AI to watch chip formation on a dirty steel lathe is actively applying the exact same principles to medical bioprinting.
I mean, it seems like a massive leap from forging metal brackets to medicine.
Yeah.
But when you look at the mechanism, the core philosophy is identical.
Absolutely identical. Think about what a bioprinter is. It is a highly precise piece of hardware that extrudes biological material living cells layer by layer to construct tissue. But biological material is incredibly fickle. If the extrusion nozzle clogs or the temperature fluctuates by a single degree, the cells die. A $10,000 cell culture is ruined.
Which is exactly the same problem as a machine tool breaking and ruining a piece of steel, just with infinitely higher stakes.
Exactly. So how do you fix it? You use the same restorative engineering. You bridge the physical hardware with digital intelligence. You install micro cameras and computer vision models to watch the extrusion nozzle in real time.
Wow.
The AI predicts the clog before it happens and adjusts the pressure, optimizing the operation quietly.
In the factory, they engineer systems to prevent catastrophic machine downtime. In bioprinting, they engineer tissue to prevent catastrophic human downtime.
The text sums it up beautifully. We engineer organs before the clock runs out. Hope becomes tangible. Whether you are stabilizing an MSME's balance sheet so a worker can keep their job, or stabilizing a cell culture so a patient can get a tissue graft, technology's ultimate purpose is to buy humans more time and reduce suffering. It must solve the problem without demanding the spotlight.
It requires immense humility from the engineer. You aren't building a flashy consumer app, you are building invisible infrastructure, which basically sets up my absolute favorite detail from this entire stack of sources.
I know exactly the one you mean.
It's this charming, self-deprecating note the engineer leaves at the bottom of their posts. Despite the fact that this engineer is building localized edge AI compliance engines, programming collaborative robots to handle high explosives, and developing computer vision systems for medical bioprinters that create living human tissue, the engineer writes, my mother still thinks I fixed desktop printers.
And then the punchline, they add, she is partially correct.
I love that so much, because she is partially correct. They aren't fixing plastic inkjets that have paper jams. They are fixing the printers of human and industrial potential.
Right.
They are unclogging the ink of capital flow in Nagpur. They are repairing the mechanism of hope in the medical lab. It's all the same fundamental maintenance.
It is a profound, grounding way to look at the work. So as we pull all of these threads together, let's just recap the journey we've taken today through the Vidarbha region.
Right. We started with the macro view. We looked at the immense, undeniable power of the MSME sector in Nagpur. We saw how these localized businesses, the small food processors, the textile mills, the foundries, are the vital spark plugs and oil filters, keeping the massive engine blocks of the large-scale industries running.
They provide the ancillary products and the massive employment base that drives the regional economy.
But we discovered the paradox. We analyzed the research showing that abundant physical resources, the steel, the coal, the available labor do not automatically translate to economic growth, because physical abundance means absolutely nothing if a business is operationally isolated and cannot access capital.
And we identified the invisible wall blocking that capital, the analog bottleneck. We saw how the reliance on manual, error-prone paperwork creates a scenario where risk scales linearly with production.
The handwritten shoebox of receipts makes these businesses appear infinitely risky to modern banking infrastructure, effectively locking them out of the loans they need to grow.
And finally, we explored the cure. We broke down the mechanics of restorative engineering. We saw how the Nano Banana 3 architecture uses inexpensive cameras, local Jetson nano edge processors, and quantized LLMs to instantly translate the physical reality of a legacy machine into mathematically verified, cryptographically secure digital data.
And we saw how that localized intelligence, maintaining strict data sovereignty, not only grants the early adopter a massive asymmetric advantage over their competitors, but more importantly, restores safety and dignity to the workers on the floor. It eliminates the fear from the execution.
So we want to connect this entire journey back to you, the listener, because this isn't just a story about steel mills in India or bioprinters in a lab. This is about the universal friction between reality and data.
Exactly. Ask yourself, regardless of what industry you work in, whether you are in software, logistics, education, or healthcare, what is the analog bottleneck in your own workflow? Where are you relying on a manual, high-friction, error-prone translation of reality that is secretly slowing down your growth?
Where are you forced to scale your risk linearly every time you try to expand? Where is your shoebox full of receipts?
Find that bottleneck, because the moment you find it and figure out how to automate the verification of that truth, you find the key to your own asymmetric advantage. And as we wrap up this deep dive, I want to leave you with a final provocative puzzle to mull over. Something that builds on everything we've discussed today about capital, data, and the nature of proof.
It fundamentally comes down to a question of trust infrastructure.
Exactly.
Mm.
For centuries, the global economy has run on human trust. A signature on a piece of paper, a stamp from a notary. But if localized edge AI and embedded large language models can perfectly and unalterably translate physical reality into compliant data.
Right, if a camera and a microchip can instantly verify the absolute truth on the ground with zero data latency, what happens to the massive global economy of intermediaries?
Think of the millions of jobs dedicated purely to translation and verification. The compliance officers, the safety auditors, the risk assessors, the middlemen whose entire economic value is derived from mitigating human imperfection.
As machines become the ultimate undeniable arbiters of verifiable truth, how will human trust be redefined?
When an AI's encrypted PDF is trusted intrinsically more than a human being's sworn signature, what does the new global economy look like? Are we building a more honest world, or just a more rigidly mathematical one? Think about that. Until next time, keep diving deep.